What I'm hoping to do is show you today, recap. What we ended with yesterday was this Blum, Liggett, and Roth algorithm, the algorithm that samples databases. And we saw it had error, something like additive error over a set of, it gets a set of queries, large set of queries Q as its input, and then it has error, non-trivial, in particular sublinear additive error on all of the queries simultaneously, so error n to the 2/3. That was very interesting. The catch for the algorithm, or the place where we were less happy, was its running time. So its running time was very, very large, particular exponential in the size of U, the data universe, so the universe from which people are drawn. That's a double exponential in the data dimensionality. And today what I want to show you is this private multiplicative weights algorithm, which has various distinctions. There's a little bit of, it doesn't get, this algorithm got pure privacy. This is going to be epsilon delta privacy. But for that, we're going to get an online algorithm. So it won't have to know the set of queries in advance. It can just keep on answering more and more queries as you feed them into the algorithm. The error is going to be smaller, so root n, a root n-ish error. And in particular, if you remember, we said that we can't, even if we want to answer n, a linear number of queries, we can't get error that's less than root n. Okay, so here we're very, very close to the root n, and we can answer a very large number of queries. The running time is going to be exponentially improved compared to BLR, so it's going to be polynomial in the number of queries you want to answer. I mean, you need to read the queries, polynomial in the database size, but also, and this will be, we'll talk about it, this is the catch for this algorithm, it's polynomial in the size of the data universe. Okay, so if we're talking about, say, d-dimensional data, this term might seem innocuous, but actually we're talking about a universe of size that's exponential in d. Okay, so oh, just if you end up processing, I should call this just k, the number of queries. If you end up, yes, it's a number of queries, exactly. Yes, yes. So this is just the number of queries you process. Right. And basically, what I want to do today is show you this algorithm, prove to you that it's accurate and private. And then in the lecture tomorrow, I think we'll move on to something quite different. Okay. So that's a theorem I want to show. This is work with Moritz Hart, showing you can answer k queries in interactive online setting with error that only depends logarithmically on the number of queries, or the square root of the log of the number of queries and square root of n. Notice, if we contrast this with adding independent noise, so adding independent Laplace noise or Gaussian noise, if we wanted to answer k queries, the error we would need would be root k, and that's optimal if you want to add independent noise. And so one way of thinking about this, at least intuitively, is that the algorithm isn't adding, it's getting the queries one by one, but it isn't just adding independent noise in order to produce the answers, it's doing something more clever. In particular, the noise that it's adding to different queries is going to be correlated rather than independent. Okay, and we know that in pretty much all of the parameters, this algorithm is optimal in terms of what you can do for general classes of queries. So before I... So I think, so answering in parallel is easier than answering them one by one. So you get a set of queries and you can process them one by one and produce all the answers. You can't distribute this algorithm. So I mean, maybe that's what you're saying. Yeah, and there's actually work on that, of showing there is kind of a distributed implementation. There are lower bounds, but this requires this sort of centralized authority that is correlating all of the noise to all the different queries. Yeah, there's been work on that specific question. Okay. So before I present the algorithm, and I sort of made this, I talked a little bit about this in the open problem session yesterday, but the view that we'll take in the talk today and in the algorithm is viewing the data set, the database, as a distribution over the universe, okay, the universe of all possible people. So the size of this universe is going to be capital N. Okay, distinguish that from little n, which is the size of the data set. So it's a very large universe. And we view any data set as simply a distribution over this universe that gives weight 1 over n to each person in the data set. And if the same person appears twice, then they get weight 2 over little n. Okay, so in this way, we just identify data sets with distributions over the data universe where small databases have small support. They're distributions with small support. The mass of the distribution at any location I is the number of people of type I or items of type I divided by n. Statistical queries, counting queries, the queries we want to answer, we view them as just Boolean n-dimensional vectors. Okay, so 0 and vectors of dimension n. And now the answer to any query that we're asked is simply the inner product between the query and the database. Okay, so to answer a query, which is basically specified by a predicate, saying whether every type satisfies the predicate or doesn't satisfy the predicate. If we take the inner product of the query vector with the data set distribution, we'll get the fraction of the mass of the distribution that satisfies the predicate. And if we want to scale our answers between 0 and n to do counts, we simply multiply this by n. Okay, so far so good? Okay, so with this view in mind, let me show you the algorithm. It's a pretty simple algorithm, so we'll actually go through it in a single slide. And what the algorithm does is it has some noise magnitude sigma. These are parameters that are set in advance, and an error threshold, capital T. We'll specify those parameters as we go along. And the algorithm is very simple. It starts it maintains some hypothesis on what the data set actually looks like. Yep. Yes. So the algorithm is going to be given the queries one by one, and it's going to produce answers one by one on each query that it's given. So what this algorithm does is it maintains some hypothesis or some idea of what the distribution, what the actual data set looks like. Now, of course, the algorithm, it's an algorithm, it has the data set, it could look at it, but we don't want to look directly at the data set because we want to preserve privacy. So this algorithm is going to only very rarely and in a very careful way ever touch the data. Most of what it's going to be doing is maintaining some hypothesis of what the database, of what the data set actually looks like, and this hypothesis is privacy preserving. It can be completely public. Okay. So initially, the algorithm has no idea what the data set looks like, so it's just going to say that the data is uniformly random over the universe. Okay. It's going to start assuming that the data set is a uniformly random distribution over the data universe, and it's going to set some error threshold T0, and then it's going to process the queries one by one. So the queries come in, query 0, query 1, up to query k. And in every query, what the algorithm is going to do is it's going to compute a noisy answer. So it's just going to add independent noise. So compute the correct answer on the data set. Here we're touching the real data set, D, and add some independent noise to it. That gives us a noisy answer. Now, remember, I told you we don't simply want to release noisy answers. That's going to sort of give away privacy very rapidly. So the algorithm uses this noisy answer in a very careful way. The first thing it does, it simply checks whether its current hypothesis, that's dt, so we started with uniforms, the uniform, it sees whether that hypothesis is pretty close. It checks whether that hypothesis is pretty close to the noisy answer. If the current hypothesis is pretty close to the noisy answer, and the current hypothesis is public, you can simply use the current hypothesis and generate that as your answer. Okay? So what we did here, and it's important to make this distinction, we computed a noisy answer on the real data set, but the only thing we used that for was to check how well our current hypothesis is doing, on the given query. If the current hypothesis is good, we simply use it, we output that value, and we don't do anything. We maintain our hypothesis and also this threshold. So we compare the difference between the query answer, between the noisy query answer and the current hypothesis to some threshold. If the difference is below that threshold, we just we use the current hypothesis, and we don't do anything. We maintain our threshold, we keep our current hypothesis. So that's great, but of course, we had no idea what the database looked like. We started with just a uniformly random data set. Why should this be the case? Why why should the current hypothesis do well? So we need to handle the case that it doesn't. And when it doesn't do well, we simply output, we can't do much. Our hypothesis isn't good, so we need to actually go to the data set. We produce a noisy answer, and that's going to be our output. That's going to be our answer for the current query. But then we're going to learn from it. So I use new noise, so that's subtle. I mean, you could output A, but then proving privacy becomes a little more complicated. So to make proving privacy easy, I'm just adding fresh independent noise. But that's not a big distinction. You can think of it as just outputting A. So sadly, we had to go to the database, we had to add noise, we had to produce that output. That sort of blows a part of our privacy budget. But then we're going to learn from that. Okay? Now we know that our current hypothesis is very far from the real database. Right? We had a big error. So we're going to update our hypothesis and make some progress. And hopefully this won't happen. What we'll show is that this won't happen too often. Okay? We have a very small bound on the number of times that we need to actually update our hypothesis. Okay, so we update our hypothesis. That's done using a multiplicative weights update, for those of you who are familiar with it, and I'll go over it in a minute. We also, for technical reasons, for proving privacy, we need to draw a new threshold. So rather than using the same threshold always to check whether our noisy answer is good or bad, every time we do an update, we also add some noise to the threshold, and we use a noisy threshold for the comparison. That comes up in the proof of privacy. But think about these noises as being pretty small. So really we're... The same threshold. I mean, the same magnitude of noise is added every time. So, yeah. It could be smaller, it could be bigger. You should think of it as about the same. The magnitude of the noise is smaller than the magnitude of the threshold. So sort of we're around the same threshold. Maybe it grows a little, maybe it shrinks a little. That comes up in the proof of privacy. So that's the algorithm. We use it to answer, any set of K queries. Hopefully, it looks pretty convincing that it gives you good accuracy bounds. We'll go over that. The question is why in the world would this be a private algorithm? And that's going to be a little bit harder to prove, but not too hard. So we'll manage to do it, I think, today. For the update, just to tell you what the multiplicative weights update is. So we have our current hypothesis d sub t, and now basically what we're going to do is we're going to increase the weight of some of the items and decrease the weight of the other items. And we're going to do this using a multiplicative update rule. So the items whose weight is increased get their weight increased by e to the eta, where eta again is a parameter that we'll talk about. And the items whose weight is decreased are decreased by a multiplicative e to the eta factor. Intuitively, what you should think of is, okay, if our answer was too small, then we need to increase the weight of items that satisfy the current predicate and decrease the weight of items that don't satisfy it. And if our answer was too big, then we want to decrease the weight of items that satisfied the predicate and increase the weight of items that didn't satisfy it. So that we're moving our data set, our current hypothesis, closer to the true answer. Yep. Sorry? If QDT was bigger than, so Q of I appears here. That's plus or minus 1. That's whether the item I satisfies the query or not. Yeah. So pictorially, let's look at the way it looks at step T. So we have the real database D, and we have the current hypothesis D sub T, that's in blue. And we have the current query, so some items satisfy the query and some don't. Okay, the big green lines where a query is 1 are items that are satisfied, and where you don't see a green line, it's not satisfied. And now, if our current hypothesis was too small, if the answer it gave was too small, then what we need to do is increase the weight of items that satisfy the predicate and decrease the weight of items that don't. And that's what our multiplicative weights algorithm will do. So it gets us a new distribution by increasing and decreasing these weights. Sorry, I'll go back. I'll just say that, so this is the increase and the decrease, and then we also need to normalize. So this is all unnormalized, and then we'll need to normalize the distribution dt plus 1. Good. So hopefully that's clear. Now for utility, I didn't tell you what a bunch of the parameters were. So the parameters I didn't tell you about were the threshold t that we use, the noise sigma that we use, and this multiplicative update parameter, eta. So eta basically governs how dramatic a change we make when the current hypothesis is bad. For utility, I'll only need to specify for you what the threshold is. So the threshold looks something like root n times log k, which is the error bound we're shooting for. The noise magnitude is a little bit smaller, so it's root n divided by log k. And what this means is that since we're answering k queries and we're using we're using Laplace noise, we know that with high probability over all of the k queries, the noise magnitude is never larger than root n times log k. That's the only thing we need to use. Okay, so almost always the magnitude of the noise that we draw is smaller than root n times log k, and in particular the magnitude of the noise is always smaller than this threshold. Okay? With high probability, the magnitude of the noise is always smaller than the threshold over all k queries. So with that in mind, let's look at the error of this algorithm. So we have two cases. Okay, the first case, our comparison tells us that our answer is pretty close. Okay, so the difference between the true answer with some noise and the current answer we get is smaller than the threshold. Since the noise that we're adding to both to the answer and to the threshold is much smaller than root n times log k, when the comparison tells us, when the noisy comparison tells us that we're doing well, usually we should, or with high probability, we really are always doing well, and the answer that we output according to the current hypothesis really is a good answer. Okay, so in case one, we're kind of golden. It works out well. And are you going to reveal information about which case you generate that? Yes, I'm assuming, so you're going ahead to privacy, and I'm just talking about utility, but I'm assuming that, so... No, I'm talking about privacy, because the thing is that if you know... It is a problem for privacy, but you're rushing ahead. I just want to talk about utility. Just utility. Yeah, so I just want to say that the error is small. And case one is a problem for privacy, and we'll talk about it. Okay. So the good thing is, since in all of the rounds, in all of the queries that we're answering with high probability, the noise magnitude is small, we know that whenever this case comes up, really the current hypothesis really is doing well compared to the true data set. And when we release this answer according to the current hypothesis, that's a low error answer. The second case, naturally things are very good. We're just taking the true answer and adding noise to it. We know that the noise magnitude is pretty small, so here also we're always doing pretty well. So utility is sort of obvious. The question is, why in the world should this algorithm be private? And as Anoop was saying, let's look at where this algorithm is actually accessing the real data set. Okay, so certainly it's accessing the data set here, but hopefully update rounds are very few and far between. So this isn't going to come at a big cost to privacy. The thing that you should worry about is that here, on every single query, and think of this as an exponential number of queries, on every single query, we are accessing the database in order to decide whether the current hypothesis is doing well or not. So we're revealing a bit of information about the true database in every single round on answering every single query. And somehow that will come for free. Okay? So somehow we need to show that that comes for free, that that doesn't cost anything in privacy. That's sort of the magic of the algorithm. Okay. So we have utility, we have utility. What we want to show is privacy. So for privacy, what I want to do is to think about the run of this algorithm. So the algorithm runs to answer many, many queries, k queries, and I want to think of its running time as divided into epochs. Okay. So I'm just dividing it into these epochs, these stages, and every time I'm going to say that an epoch ends when we have an update. Okay? So when the update happens, we end the current epoch and a new epoch begins. Okay, so pictorially, the way this looks, or the way I want you to think about this, is we have this algorithm. It's running over many, many queries. So query 1 comes in, query 2 comes in, etc. At some point, there's an update, in some query j. And then we say that the current epoch has ended. Okay? And in these epochs, what happens is that the algorithm is always given as input the current hypothesis. Okay? So in the beginning, the first epoch, the current hypothesis is just uniform distribution. And that's public. So The algorithm's inputs are the current hypothesis, and the private input, the input it's supposed to protect, is the data set. Okay, and then the algorithm runs. In this epoch, it produces an answer, answer 1, answer 2, answer 3, etc. And in the end, at the end of the epoch, it outputs the current updated hypothesis. So here that would be D1. Okay? And I'm assuming that everything that happens here below this dotted line is public. So we may as well, even though the algorithm itself, as I specified, it doesn't release the current hypothesis every time, let's assume for free that it's releasing it. And I'll prove that it's private even if it releases the hypothesis. So certainly if it doesn't release the current hypothesis, it's also private. Okay. So that epoch ends, and now we think of this as a new epoch beginning. So we have the current hypothesis, and we work with the data set, and we release answers. This is AJ plus 1, etc. And the reason I want to do this division into epochs is that I actually want to think about the algorithm, this as the composition of many algorithms. Okay, if a single algorithm that runs up until the update, and then the algorithm sort of stops running, and we do a new run of it. So I actually think about this, even though it's all one algorithm, I think about it as an algorithm A0 that's running, and then an algorithm A1 that's running for the second epoch, etc. And I'm going to use composition. So what I'm going to show is that each of these algorithms on its own, up to a single update, is very private. And then since all we're doing is running one of these algorithms for every update that we get, if we can show that there are a few updates, then we'll know that the whole algorithm put together is also private. So the proof of privacy will just be based on two simple lemmas, or simple to state lemmas. What we'll show is that each epoch on its own is very private, so something like root log k over n, differentially private, with pure differential privacy. And the second lemma will show is that with high probability, the number of updates is small. Okay, so intuitively, every time there's an update, we make a lot of progress, and so there can't be too many updates. And then simply by composition, remember by the advanced composition that we said yesterday, we know that really what we lose in each of these epochs is something like this squared. So in every epoch, really what we lose is something like log k over n privacy, and taken over n over log k epochs, we get differential privacy for the entire algorithm. Okay, so everyone's very quiet today. Either I'm being completely clear or you're all sleepy. Yes? Yes? So in the composition result, as I stated it was deterministic, but in fact, the composition bounds hold even for an adaptive adversary who decides how many mechanisms to run and decides what mechanisms to run on the fly. So the composition is powerful enough to handle this type of scenario. It's a good question. Okay. So what I want to do is to prove these two lemmas. Neither one of them is terribly hard. So that is what we'll do. And for privacy, I'm going to mainly do a proof by picture, and hopefully that'll be clear. That'll be clear enough. Okay. So this is our algorithm. All we want to show is that this algorithm for a single epoch is differentially private. What it does is you start with some, in the teeth epoch, you start with some distribution that you're given as input. I'm fixing the threshold, so we have this noisy threshold that the algorithm is choosing and fixing for the entire epoch. And then we get our queries one by one, and we repeat, we run the algorithm until we get an update, so we compute a noisy answer, and we do our check. We check if the noisy answer is pretty good. If it is, then we just move to the next query. And if it isn't, then the epoch ends, so we output a fresh noisy answer. We run the update algorithm, and we output the new hypothesis. And what we want to show is that this algorithm is differentially private. Okay? And the way we'll do it is by picture. So what I want us to think about is this is kind of the error axis, and this is the time axis where the queries come in. And this is, suppose this is the noisy threshold T. So this is the error that we're willing to live with, or the error that we compare to. And now the queries come in one by one, so query 1 comes in, and the true error on query 1, suppose, is somewhere here. Okay, so that's the error on query 1, that's QT on D minus QT on DT, an absolute value. So that's the true error. What we're doing up here, we're adding a little bit of noise to the answer, to the true answer. So when we look at this difference between the noisy answer, the noisy true answer, and the answer by the current hypothesis, we're going to get some shift. Okay, so maybe the error that we see is going to be up here because we had positive noise. Right? So this is the noise, let's call it sigma 1. But that's still below the threshold, so all we do is we output according to the current hypothesis and we move on. Okay. Second query comes in, suppose its error is a little bit bigger, but maybe the noise was negative, so actually what we're seeing is down here. Again, it's below the noisy threshold, and now a third query comes in, and for that, actually the error is above the threshold. The real error is above the threshold. But lucky enough for us, we had some negative noise, so it ends up being below the threshold, so we don't update. We just keep going, et cetera, and then maybe here the epoch ends, we have a query that's above the threshold, and the noise is positive, so the noisy error is above the threshold, and we end the epoch. We update the database, the current distribution, and we end the epoch. Okay. So what I want to show is privacy. So suppose what I want to show is that we have a certain data set D, and suppose this is the behavior for D. Now the question is, what's the probability of this behavior if I look at an adjacent data set D prime? So maybe this is just below the threshold. So notice already that on D prime, the behavior might change. For example, it might be the case that this noisy error that was just below the threshold on D will suddenly be, if we use the same noise on D prime, it would be above the threshold, it would lead to an update, and the behavior would look quite different. Okay, so that would be the concern. So what do I want to say? I want to say, what do I want? I want two things. I want that for every query or round where there wasn't an update on D, there also shouldn't be an update on D prime. And then in the last round, when there was an update on D, I want that there will be an update on D prime. Right? I want to guarantee these two things. And I want to say that we can do that using very small changes to the noise. Okay? Because I can make small changes to the noise without changing the probability of the event of this all happening by too much. But I can't make big changes, or I can't make many changes to many of the noise values. That would be a problem. I can make small changes to a few of the noise variables, right? Because it's a Laplace noise, so changing the magnitude by 1 doesn't change the probability of seeing that noise value by too much. But I can't make big changes to any noise variables, and I can't make many small changes because that would lead to the privacy losses would add up. So I want to say that the probability that D prime produces this exact behavior is about the same as the probability that D did. So in particular, what I actually want to do is create a bijection between all the noise values that produce this behavior on D and the noise values that produce this behavior on D prime, and say that the bijection, the probabilities are about the same in this bijection. It matches noise values with similar probabilities. But I'm not doing the whole bijection, I'm just talking about a single scenario where we had certain noise values for D, and I want to say that with very small changes to the noise values, we can guarantee the same behavior to D prime. And intuitively, this means that the event happens with about the same probability for D prime. Okay? So the concern is that there could be many rounds. It could be that there are lots of updates. At least the intuitive concern that I want to handle is that there could be lots and lots of updates that are hovering around this update threshold, but didn't quite lead to an update on D. Didn't quite lead to an update on D, but would lead to an update on D prime. And I don't want to change the noise independently for each of these almost updates. So instead, what I'll do, and that's where the noisy threshold comes in. Remember, we had this threshold. This threshold was a noisy threshold. So the real threshold, presumably, is somewhere here. And we picked a noisy threshold by adding some noise to it. Okay. When in the run on D. And in order to guarantee that every single one of the rounds that didn't lead to an update on D also doesn't lead to an update on D prime, all I need to do is to increase this single noise for the noisy threshold by 1. So by making this small change to the noisy threshold, I immediately guarantee that on every round that there wasn't an update on D, there also wasn't an update on D prime, because the error on D prime can only change by a little bit. So if I increase the in particular the error, even if we keep exactly the same noise values, the same sigmas for the noisy answers, the error magnitude can only increase by 1 when we go from D to D prime. Okay? Because the answer on D and on D prime can only differ by 1. So if I increase the error threshold by 1, I'm immediately guaranteeing that every round that didn't lead to an update on D also won't lead to an update on D prime. And the nice thing about this is that I'm doing this with a single small change to a single draw from the Laplace distribution. And that's giving me that's keeping me safe for all of the rounds for the entire epoch up until the last update. Okay? Now on the last update, it could very well be the case that, since now I increased the noisy threshold when I was thinking in the run on D prime, it could be that the round that led to an update on D won't lead to an update on D prime. That's a concern, and I want to have the same behavior. So I want to make a change, but the change that I'll make is only, this is suppose on query Qj. So now all I need to do is to change the noise magnitude, this noise magnitude, sigma j, for the last query. And what I'll do is I can just change the noise magnitude by 2 now. 1 potentially to make up for any difference between D and D prime. So it could be that just because of a difference between D and D prime, you wouldn't get an update on D prime even using the same noise and the same threshold. So I need to change the noise magnitude for this last query by 1 in order to make up for any difference between D and D prime, and then by another 1 to make up for the difference in the thresholds that I chose. So basically all I'm doing is I'm changing the threshold noise. Let's call that sigma capital T. I'm increasing it by 1, and the noise for the last round I'm either increasing or decreasing by 2. And now I'm guaranteed that on every round where there wasn't an update on D, there won't be an update on D prime. And in the last round where there is an update on D, there will also be an update on D prime. So does anyone see that anything is missing? Yeah, so basically, the algorithm is randomized whether it runs on D or on D prime. What I'm trying to show is that for any event that can happen on D, it happens with about the same probability on D prime. And the way this is formalized is by saying, well, for any noise values that led to a certain outcome on D, I can make small changes to those noise values and get the same outcome on D prime. And because the changes are small, even if they're deterministic, because the changes are small, that means that the probability of seeing those noise values that would lead to the outcome on D prime is about the same as the probability of seeing those noise values on D. So think about it this way. If I'm just releasing a noisy answer, okay, so again, I'm releasing the number of people in the room who have heart disease plus some noise. If you look at, and this produces a certain distribution, I want to say that I get the same distribution even if we take me out of the room and suppose I have heart disease. So that means that for every noise value that we got when I was in the room, I can sort of map it to, I can change the noise value a little bit by adding 1, so I'm changing it in a deterministic way in order to get the same outcome even when I'm not in the room. So the change is deterministic. It's sort of creating a bijection between noise values. And the point is that the probabilities of these noise values that are being mapped to each other in a deterministic way is about the same. Yeah. Yeah, so it's infinite in both. It's actually important that the noise can go, from minus infinity to plus infinity, because then we can create these bijections. So increasing by 1, simply, you're taking, the range minus infinity to infinity and shifting it by 1, still minus infinity to infinity.
Version 1 was like a coupling between the answers for D and D prime, so that
yes,
the metric close and that metric governs
the probabilities. Exactly. Yeah, I think of it as a bijection, but you can probably think of it as a coupling, and I think that's fine. So, why is it addition, but why is it epsilon, delta, and epsilon? This is epsilon. The delta only comes in when we're doing composition across the many epochs. So this, you're exactly right. This is perfect privacy, and the delta comes in when we're doing, just from the Azuma, when we're doing composition over many epochs. Okay, so no one has objected so far, and Anoop, you should have objected. Oh, sorry? Sorry? Yes. Sorry? Yeah, so I guess maybe I'll go back to the update. So the update didn't depend on the data set, remember? So go back a bit. It's a good question. So this update rule, the change between dt and dt plus 1 didn't actually depend on the database D. All it depended on was the sign of your error, up or down. And we can release that, that's maintained, so that's fine. Yeah. So that's why we can sort of think of this hypothesis as being public. Okay, so the objection that no one is making, and Anoop, you should be making, has to do with why we drew the fresh noise here. It's not a very important thing, but I also want to release this last answer on the query that ends the epoch. And to do that, since I already used, I need to add fresh noise, otherwise it's gonna look differently. That answer is gonna look differently for the database D and D prime. That's why we're adding independent noise there. In the last round, when we're actually releasing the answer, we're using fresh noise. Basically because the bijection, the change in the noise that I use in order to make sure that this comparison goes the same way won't necessarily give the same answer, the same exact answer on the two data sets. And so, because we move the threshold, basically. It's a different threshold, it might not give exactly the same answer. So just to be safe, I'm using fresh noise now. I should say, by the way, that this proof of privacy is actually due to, so it's a simplified proof. The original proof we had was less modular. It got slightly better parameters or better constants, but it was less modular. And the proof of doing this simply by composition is due to Dwork and Roth, and it appears in the book, in the Dwork and Roth book. I showed you the reference last time. Next you'll release D1. Yep. And then we'll set the sign. Yeah, so the sign is already sort of, the sign comes for free once we've guaranteed that just the fact that there was an update is public, that the direction of that update is always the same. between D and D prime because you're really far away. You know, your error is way above a threshold. The sign can't be different between D and D prime. It can't jump all the way to the other side of the threshold. So that sign comes for free. Okay. So that's the first lemma. The second lemma that I need to show you. So now we showed, and as was pointed out, this is pure differential privacy for each epoch on its own. Now all we need to show is that with high probability there are not too many epochs, and then just by advanced composition we get privacy for the entire algorithm put together. So, and this is kind of where, sorry, grab this water. This is where we use the multiplicative weights update. We never used it so far. And if you're familiar with multiplicative weights update algorithms, this shouldn't be too surprising for you. We know that these kind of multiplicative weights very quickly converge to good answers or good behavior. And this is done all over the place in optimization and learning theory. But let's see how it comes into play here. Okay. So I want to show with high probability there are at most n over log k epochs, and this is proved using a potential argument. And what I'm going to do is I'm going to assign I'm going to use a potential function. So this psi of whatever my current hypothesis is, which is simply the KL divergence between the true database viewed as a distribution and the current hypothesis. Okay, so that's going to be my potential function. So the first thing that you should, the first thing we can observe so since we already know and love this fact from yesterday, we know that psi of dt is always above 0. Okay. What I claim is that psi of d0 is at most log of the universe size. Okay, so d0 is just a uniform distribution over the universe. And so the KL divergence between the true distribution D and the uniform distribution, that's essentially log U minus the entropy of D. The entropy of D is always non-negative, so it can be at most log of U. And what we'll show is that every time there's an update, we make progress. Okay, so the data set is really getting closer in some rigorous sense to the current hypothesis is getting closer to the true data set. And in particular, we have a significant drop in the potential. Okay. There isn't. The only tiny thing that's different is that, well, I don't know if it's different. I don't know if it's been observed or not in that community, is that here we're sort of in a binary regime. Either we have big error and we want to say that we make big progress, or we have small error and then we do nothing. Whereas usually it's more continuous. I mean, the multiplicative weights that I know is more continuous. You sort of continually are updating scale to the error that you get. And we don't want to do that here, because we don't want to reveal the direction of the error in every round. So yeah, we actually can't do that. That wouldn't be privacy preserving. So really it's a slightly, it's a twist on the analysis showing that relating the error that you have to the potential drop in that particular round. But more or less, I mean.
So I guess what I'm saying is, there are many proofs for multiplicative weights, many things that follow like a similar argument.
Right.
Are there some update rules that work for standard application of multiplicative weights, but do not work in differential privacy context? See, for example, like one of my other favorites is like there's something follow the leader, follow the preferred leader.
Mm-hmm. Right. So
actually have the same. So here, there's something a little funny, right? Because you're adding noise inside the thresholds, but in your like outer thing, you're doing multiplicative weights. Which there are ways to get those guarantees where they're adding noise and they look similar to what's going on.
Yeah, and in fact, we have in a different context, we have a privacy-preserving follow the perturbed leader algorithm. So I'm not sure. I mean, I don't have an encyclopedic, certainly I'm far from having an encyclopedic knowledge of all the ways and places that multiplicative weights is used, or these online algorithms, the various online algorithms. I don't see, particularly for follow the perturbed leader, I don't see how that would really work here. I mean, I think here it's important that we're maintaining a distribution. If you wanted to use follow the perturbed leader, maybe you would have to start thinking about all the... So usually with follow the perturbed leader, you have a set of candidates, and you're following the one that's done best so far, right? But it's perturbed. Perturbed, yes, yes, yes. You're not going to choose. You're going to add some noise and then follow the noisy maximum leader. So here, if you wanted to talk about candidates to follow, we're talking about you want to act according to a certain distribution, so you'd have to start enumerating over all possible distributions over data sets, I think, which would increase your search space exponentially. If you did do that, you could still get something non-trivial, and I'm not sure whether we can prove privacy for that or how to prove privacy for that version. So you wouldn't get parameters that are as good. And it's a good question how you would add the noise. I mean, I think you would have to do something similar to this noisy threshold in order to guarantee privacy, and I'm not sure how you would do that. Yeah, in particular, I mean, it could be the case that there are two candidate leaders to follow, and one of them is a little bit better for D than for D prime. And now you're going to go over you're going to go round by round by round, and every time you're going to make an independent choice whether to follow the first one or the second one, you're going to keep losing privacy.
I mean, I guess I'm just curious whether there's something underneath what you're saying of take any multiplicative weights algorithm, if it has block property, then it's good enough for us. It would be interesting to understand what the extra constraints are. Yeah,
I agree. I don't, yeah. Yeah, so I don't know of a general transformation from, I don't know about multiplicative weights. That seems like a technical property of the algorithm. But I don't know how to formulate a meta theorem going from low regret to privacy. I suspect something like that may be possible, but it hasn't been done. Yeah. I mean, the algorithm, the multiplicative weights algorithm on its own doesn't have privacy. You need to carefully choose how you're adding noise in order to make it privacy preserving. And in particular, you need to, I don't know how to prove its privacy. This is a little bit ridiculous, but the proof of privacy I gave you doesn't go through unless you use the same threshold for the entire epoch, right? Like that's a particular thing we need to do in order to guarantee privacy in this way. So I think what one could hope for is a theorem saying, any low regret algorithm can be tweaked in this way in order to make it private. I don't know of such a meta theorem. Okay, so the claim is that we have this potential function. Sorry, that was a bit of a digression, but we have this potential function, and the claim is that on update rounds, the drop in potential is pretty significant. So we haven't talked about eta at all. Eta is the scaling parameter for the multiplicative weights reweighting. And it controls how quickly the potential, drops. In particular, the potential drops by at least eta times the error in that round, minus eta squared. Okay, so this is a claim that we need to prove. In particular, I'm going to assume that the error is always at least t over 2 in update rounds. So remember, we're doing updates based on some noisy error. We're doing updates based on some noisy approximation of the error, but because the noise is small and the threshold is big enough, I can assume that when we have a noisy update, really the true difference, there really is a difference between the database and the current hypothesis, and I'll assume that distance is at least half of the threshold. Okay, so with this in mind, we can simply take take eta to be something like the threshold over 100n. That ends up working out. I think I'm missing, by the way, a divided by n factor. So this is for absolute error, and what I want is fractional error. So you should have this divided by n. Then you take eta equal to t over 100n, and you get that the potential drop is something like t over n squared. Which again, sorry, a bunch of typos on this slide. So this should be log k divided by n. About log k divided by n, and that tells you that in every round there's an update, your potential drops by log k divided by n, so you presumably will have just about n over log k update rounds, which is what we wanted to show. I'm ignoring the log u factor. So really the number of rounds you'll have is this times log u. But I'm putting that inside the O tilde. So think about this as something small, like 1, and then the number of rounds you have is n over log k. Yes. So actually the error of the algorithm, just to keep it simple, I've focused on these parameters, but the actual error grows as something like root n times log k times, if you choose your parameters correctly, it's actually log u to the 1/4, all of that divided by epsilon. But I'm ignoring epsilon and log of u for the analysis now. Sorry? Yes. U is the universe of all the possible users, so it's you know, all the possible heights, all the possible collections of attributes. Okay, so I guess I'm going to show you. Log u is potentially big, so I do think of log u as being smaller than n.
But could you hope for log of the support size of your
No.
database to begin with?
No, I believe that there are results showing that this is tight. If you want to answer general predicates, general queries. Yeah. Okay, so all we really need to do is prove this claim. I'm not going to go through all of it, but let's start and I'll just try to give you some intuition about why it's true or how you would prove it. How many of you have seen multiplicative weights analyses, the multiplicative weights algorithm? So I think it's worth doing at least a sketch, at least an overview for those of you who haven't seen these types of arguments. So let's just go through it. So we have psi. We want to bound psi of dt minus. Right. So you would need to scale your noise to log of u. That would add to your error. It would improve your privacy, and everything would go through. Yeah. So yeah, think about this now as guaranteeing something like log u privacy. So that's a very bad privacy. Maybe it's very bad, but then you add another multiplicative log u to your noise, and it takes care of it. Okay, so we want to bound this this drop in the potential. So what is that? You know, this is simply the KL divergence from d to dt minus the KL divergence from d to dt plus 1. So it's a sum over all u, d of u times the log of d of u over dt of u minus the log of d of u divided by dt plus 1 of u. Right, I'm just opening this up. Yeah, and these two cancel out when we subtract the logs. So we just get the sum of d of u times the log ratio between dt plus 1 of u and dt of u. The difference between these two distributions. Okay, I'll just do a tiny. I know we're kind of running short on time, but I'll do a tiny bit of this development in like 5 minutes and just give you a a hint of why you get this kind of behavior, why the potential drop is influenced by the error. So this ratio, dt plus 1 of u divided by dt of u, we know this is controlled by the multiplicative update. Right? The multiplicative update controls this ratio on places where dt was too, in places, again, if the answer was too small, on the locations that don't satisfy, that satisfy the predicate, dt plus 1 is larger, and on the, or grows, and on the locations where it did satisfy the predicate, dt plus 1 shrinks. Where it didn't satisfy the predicate, dt plus 1 shrinks. So it's just the sum over u. I mean, what I want us to have here is just the change, the ratio. So basically, we have one. So let's look just at dt plus 1. So that's dt of u times e to the minus eta times what I'll call the sine of u. That's just telling us whether u needs to increase or decrease. So it's plus or minus 1. Okay? If the weight needs to increase, then the sign is minus 1, and if the weight needs to decrease, then the sign is plus 1. So that's very nice because these two things cancel out. I'd love to stay with just this expression, but then I also have to take into account the normalization, right? I needed to normalize, so I also have here a 1 divided by a sum over, let's call it v in u of dtu times e to the minus eta sine. Okay, so basically what I'm going to do is I'm going to, the log of the product of these two things is the sum of the logs. So let's separate this into its two components. And what we'll have is the first component is simply going to give us the sum over u of d of u times log of e to the minus eta sine. So that's eta minus eta times the sine. Okay, that's what we get from here. And you can simply think of this as minus eta times the inner product between d and the vector of sines, whether the current hypothesis was too big or too small, depending on whether the current hypothesis was too big or too small. So that's the first component, and then the second component is going to be the sum over, let's call it v, let's still call it v, of the log of dt of u times e to the minus eta times sine of v. Sorry, my log is in the right place, in the wrong place. Say that again. Where? Yeah, that went away. So I think this is right, unless you see a mistake. Tell me if you see a mistake. Okay, so I do have a mistake. No, I don't. Good. Okay, so this is d inner product with the sign, and what I want to show is that this is something similar to dt inner product with the sign vector. Okay, so essentially this second component is going to look something like eta times the inner product of d sub t with the sign vector. That's kind of an exercise. And that's also where the eta squared comes in. We're just going to use an approximation to e to the minus eta using 1 minus eta plus eta squared. And so in the end, what you get for this difference, that's an exercise that you can do, but in the end, what you get for this difference is that it looks something like mu times the inner product of the difference between dt and d with a sign vector minus some mu squared factor. And this, if you think about it, is exactly counting the weight of the places on which, the weight of all the places on which dt and d differ, normalizing it exactly with the sign. So that's going to give you exactly the error between, or it's going to be bounded by the error between dt and d. Sorry, qt. So if anyone wants to stay in the break, we can sort of break these two calculations down, why this is proportional to the inner product of the sign of dt, the inner product of the sign with dt. And this one's pretty simple, why the inner product of the sign with a difference between dt and d is proportional to the error. Okay, and this, yeah, these kinds of multiplicative weights updates and their quick convergence are used all over the place in optimization, in learning, in algorithms. So it's a useful technique to know, or a useful kind of toolkit to know. Okay, so to sum up, we saw this private multiplicative weights algorithm, the accuracy nearly optimal in the worst case over all the queries. We got strong privacy, differential privacy. The magic, or part of the magic, is that the algorithm doesn't need to know the queries in advance. So I'm going back, and let's think about this a little bit intuitively. Rather than answer with independent noise, the algorithm exactly was really carefully correlating the noise by maintaining this hypothesis, which is usually good. So as long as the hypothesis is good, it can just answer according to the hypothesis. And then when the hypothesis is bad, we're sort of getting we're getting a lot of bang for our buck. We're paying something in privacy, but we're converging very rapidly to a good hypothesis. The running time, since we need to maintain this distribution, which is over the entire data universe, has a linear dependence on the size of the data universe. That also has been shown to be inherent under cryptographic assumptions. If you want to answer, so we know that you can answer about n squared queries with linear error, just by the advanced composition. You can scale the error to the square root of the number of queries. If you want to answer even a little bit more, so n to the 2 plus little o of 1 queries, you cannot do that unless you run exponentially in the data universe size under cryptographic assumptions. So we can cook up queries for which answering more than n squared queries is computationally hard. And in fact, this algorithm under cryptographic assumptions is optimal in its running time, or close to optimal in its running time, for general queries. Okay. Of course, the size of the universe is exponential in the number of data attributes, so that leaves us with a bit of a problem. This algorithm has actually been implemented in practice, and for data that has bounded dimensionality, it works really well, or it seems to work really well. The problem is that for big data, for multidimensional data, exponential dependence on the number of data attributes is a big problem. And I think the question in research on differential privacy, or one of the big questions, is what query sets, for what collections of queries, can we actually get polynomial running time? Okay, so we know that for arbitrary queries we can't. You can cook up, using cryptography, you can cook up some very strange queries that you can't answer efficiently. But for all the natural queries that we want to ask, the answer may well be that we can get polynomial time algorithms. And there's an interesting connection. I mean, there's kind of a moral analogy with learning theory, where we know that if you want to learn arbitrary concepts, that's computationally hard because of cryptography, but that hasn't stopped learning theory from developing both a theory of polynomial time learning algorithms for interesting classes and lots of interesting heuristics that seem to work well in practice.
So if the queries someone asks are not extremely sensitive, should I be actually worried about this lower down? Right, so if you take something like height, you can do it at whatever granularity you want. And then obviously there's some granularity when the lower bound is not actually that worrisome.
Right.
U isn't that big.
Right.
But if I ask,
so if you draw a coarse epsilon net over your universe,
6 plus root 2 inches, or
yeah. So the queries for which you should worry about it and where they actually show that privacy violations can happen are very cooked up queries. They have to do with things that, like trader tracing.
They inherently have to be very, very sensitive to.
So they do quite different things. They do things like they treat the data as a ciphertext and decrypt it. So they're not natural queries in any sense or form at this point. Okay, great. That's all I wanted to say for today. Thanks.